Hello all of you. So in the last week we discussed the free energy calculations, and towards the end of the last lecture I discussed briefly about the time scale issue and some methods that fall in this category. Particularly the methods come under the rare event simulations, non-equilibrium simulations, and then finally mesoscale simulations. So before we come to those methods, I will briefly touch upon what the time scale issue really is, and then later on we will discuss the Langevin dynamics and Brownian dynamics simulations after that. So when we are doing typical molecular dynamics simulations, let us say of an atomic system, the problem is that the time step that we can take is typically quite limited, and the reason why it is so small is because we are trying to probe the motion of the molecules actually within the molecules, and in that case we are pretty much limited by the vibration of the bonds, the angle of the bonds, and all these things which are happening at very small time scale. And therefore, if I really want to capture the true dynamics of a molecule, we really have to work at a time scale or choose a time step such that it captures these effects, the bond vibration, angle vibration, the conformation changes because of that, and so on. And that really means that in typical molecular dynamics simulations, all we could go is the times of the order of say 1 nanosecond, because the delta t is so small that we cannot really go to very long times. The second issue is that if I am looking at the liquid systems, in most cases we have plenty of solvent molecules. Let us say if I look at a solution of any compound, we are basically simulating most of the time the solvent molecules as opposed to the compound itself, because the compound is present in, for example, water, and at any significant density we will have quite a large number of water molecules to work with. In typically the water molecules that are being simulated are 10 to the power 3, 10 to the power 4 times larger than the molecules that we are interested, in fact much more, for dilute solutions. And that really means that not only I am simulating the molecule, I am simulating plenty of solvent molecules in there. Then we are interested in the equilibrium behavior, and therefore we have to simulate long enough that we can get to the equilibrium behavior. In Monte Carlo, there can be some smarter ways where I can introduce dynamics that get us faster to equilibrium, but in molecular dynamics we have to follow the true dynamics of the system, and that means that we are further limited in the equilibrium approach, because it will take some time to achieve equilibrium, and for that time we have to simulate the motion of all the molecules, and we have plenty of them. So one of the ways that we can think about addressing this problem is, why not simply take all the solvent molecules out of the box? We just consider the compound that is being considered, because ultimately we are interested in that only. That we could have done if the solvent was not playing any role between the interactions between the compound in question. And typically solvent mediates the interaction between the compound, that is one thing that solvent does, but solvent also basically have interactions with itself that contributes to the behavior of the entire solution, and therefore we cannot simply remove the solvent altogether in most of the cases, and when we remove that, the interactions are not very well captured. Then what we can do is we can remove it at the expense of adding in some kind of an effective interaction that basically somehow accounts for the effect of removed solvent, and this is where the Langevin dynamics method fits in. It essentially removes solvent, but adds some extra interactions that takes care of the solvent that has been removed. Or we can use what is known as coarse graining, in which we can try to represent molecules into like smaller units than compared to the number of atoms in the molecules. Let us say for example, if you have 10 to the power 4 atoms, I can say 10 of them form a CG unit or a coarse grained unit. So, in sense you are simulating 10 to the power 3 CG units only, but of course, now each of the CG units contain 10 atoms and we are not simulating the atoms themselves. So, we have lost some resolution. We are not looking at what is happening within those 10 atoms, we are looking at what is happening between the CG units, not the atoms itself. So, not only we have lost the resolution, but also we have to somehow again get the effect of the atoms, the interactions between atoms in our description of the coarse graining process, and that is not so trivial again. And finally, in many cases equilibrium is not what we are interested in. So, molecular dynamics is ultimately capturing the true dynamics. So, why not simulate it for phenomena where there is no equilibrium? Let us say for example, we have some external field acting on the system, and in that case clearly we can use molecular dynamics, at least intuitively, because molecular dynamics is in principle capturing the true dynamics of a system. The only problem is that when we use thermostat or barostat, it is typical that the methods are particular to the equilibrium condition only, and therefore, in any case of an applied field, we have to revise the molecular dynamics method to account for the non-equilibrium behavior that we are interested in. Having said that, one may argue that when I start my simulations and until I reach equilibrium, I do have a non-equilibrium part of my simulation. But the problem is that since the initial state is something that we do not know, that non-equilibrium part is something that we cannot assign much meaning to, because that is based on the initial state that we have chosen without the knowledge of the actual system configuration. In most cases it is arbitrary. So, although we are capturing non-equilibrium behavior until we reach equilibrium, that is not the kind of non-equilibrium behavior we are typically interested in. We are interested in non-equilibrium behavior in the presence of an applied field starting from a known initial state, and that is where the trouble comes in. So, basically the class of methods that we will discuss try to look at these problems where time scale can be an issue and we really want to simulate the effect of applied field. And the first method that I will discuss in this category is known as the non-equilibrium molecular dynamics. I will not try to go to the mathematical details of these methods, but I will like to just highlight what methods are out there, and all of these requires quite a bit of reading to learn about the methods and to apply it to practice. They are quite detailed methods. Many of these methods are still developing and better approaches are coming in to improve these methods. So, it is an ongoing research, I would say, instead of being like a standard tools out there. And many of these methods are not even implemented inside standard software. So, you may have to program it yourself, and at least in the case of coarse graining, the methods are not robust enough to be applied to any system that you want to simulate. So, the first class of methods is the non-equilibrium molecular dynamics. So, in this case, we are interested in an external field that is being applied on the system. Let us say I call it by a vector FET, and this is a 3n component vector corresponding to an n particle system. So, every particle can be experiencing not only the force due to other particles, but an applied force coming from the external field, and that force will have 3 components for every particle. So, in total the force is going to have 3n components. So, even though for example, the electric field is going to be constant, the actual force because of the electric field can be different on different particles in the system. Similarly, for magnetic field or any other field that you can think of, because it also depends on the properties of those particles, right. If it is completely passive, that means the particles do not affect the forces. In that case, it becomes somewhat easy, the force becomes constant. But if it is somewhat active, that means that if particles are playing a role on the forces acting on them, in that case it becomes quite complicated, because the forces depend on the system configuration, the coordinates of the particle, and so on and so forth. Nonetheless, we can start with the equation of motion that we had, the classical equation of motion that we used for equilibrium molecular dynamics, and add extra terms in the q dot equation and p dot equation. The q dot for the derivative of the generalized coordinates, that is the momenta, and p dot, that is the momenta derivatives. So, that is the acceleration really. And in this case, AP and AQ are going to be 3n times 3n matrices, because Fe is a 3n matrix, Qn is a 3n vector, because you have 3 coordinates for every particle multiplied by n times, and AP and AQ essentially are telling me how the field is coupling with the particle, in the sense that how the position and momenta of the particle is coupled with the external field. In the case, as I said, if it is a passive field, that will be probably a constant, but in other cases it has to be somewhat complicated. But in most cases it is not really a very large matrix, because many of the terms are 0. So, we have to work with only the terms that are non-zero in that particular matrix. So, in that cases these matrices become somewhat tractable, so as to speak. So, using the idea of this non-equilibrium molecular dynamics, we can, for example, compute the viscosity, the thermal conductivity, and diffusion coefficient by doing simulations that somehow simulates the transfer processes, because as we study in chemical engineering, there are 3 kinds of processes: the momentum transfer, in which the variable that we work with is the viscosity. Then we have heat transfer, particularly the conductive heat transfer, where the variable we work with is thermal conductivity. And then finally, we look at mass transfer, where the variable for diffusive mass transfer is the diffusion coefficient. So, we can perform numerical experiments wherein we have some momentum transport going on and measure the viscosity. We can perform a heat transfer experiment numerically and compute thermal conductivity, and we can perform the mass transfer experiments numerically, in which we can compute the diffusion coefficient. And in most cases these are going to be non-equilibrium simulations, because viscosity is a property that is defined in a dynamic manner. Thermal conductivity is also dynamic property. Diffusion coefficient is defined at equilibrium in principle, because at equilibrium also we have diffusion of molecules, but that is not always same as the diffusion coefficient out of equilibrium, and therefore, that can be also computed in a non-equilibrium simulation. The next class of methods are the mesoscale simulation methods, and here, as I said, the goal is to remove the degree of freedom, and that we can do either by removing solvent or by doing some kind of coarse graining. So, the first method in the category is the Langevin equation, that in here we pretty much remove all the solvent from the system, and we simulate the effect of solvent by adding 2 forces in the equation of motion. One is a frictional force or a drag force, and other is a random force or the thermal energy of the system. And these forces appear in the P dot equation as the red guys in here. The first is the frictional force that has a zeta, that is a friction coefficient, and the velocity of the particle, and a sigma, that is the strength of random force, and a random force term W dot, that is the time derivative of a random force, which is defined using what is known as a Wiener process. And gamma is the damping coefficient that is basically related to zeta. So, we can write this equation in terms of like zeta v or gamma p, where in one case I am keeping the velocity and in the other case I am keeping the momentum in the frictional force term, and therefore, zeta is basically mass times gamma. So, there are two ways of writing the equation for the frictional force term, and that particular term is defined as the kBT thermal energy divided by the diffusion coefficient as given in here. Finally, there is a theorem called the fluctuation dissipation theorem that says that the strength of the random force should be a function of the zeta, that is the friction coefficient, or we can write in terms of gamma as something like 2m gamma kBT, because zeta and gamma are related. So, there is a relation between sigma and zeta, and that must be satisfied. So, the random force term is quite subtle in here. So, first of all, this W has 3n components, and in fact, the time derivative W appears in the equation, and all these 3n components are independent of each other, and they are basically forming what is known as a Wiener process, and it is defined like this. So, if we look at the change in W over a small time interval dt, it is going to be a random variable with the variance equal to dt. That means, if I look at the dW, that is the change in W between times t plus dt to time t, it is going to be under root dt multiplied with another random variable g, which is going to be a Gaussian random variable with 0 mean and unit variance. So, that if I square this, I get dt, and that becomes the variance in the Wiener process. So, since the change in W is proportional to square root of dt, we should better not work with dW by dt, but we should work with dW directly, right, and that means that we can change the way we write the equation slightly, so that we do not have to compute the derivatives, because dW is a function of square root dt, and numerically it will be more convenient if we work with dW directly, and this is what we can do here. So, I write this equation. So, you can note that this is equal to dP by dt is equal to f minus zeta v plus sigma dW by dt, but I can also write it in the form dP is equal to f dt minus zeta v dt plus sigma dW, so that dW appears here as opposed to dW by dt. That is just a convenience from numerical perspective, and also because W is proportional to square root of dt. So, with this particular idea, we basically numerically integrate the equation of motion. There are methods out there similar to the velocity Worley methods we have discussed, but also taking care of the random force term and the frictional term that basically integrates the equation of motion. A very similar idea is also used in the thermostat known as the Langevin thermostat, that is often used in molecular dynamics, but Langevin dynamics itself is a whole different class of method that is used for the simulations of systems where I want to simulate at larger length and time scales. Since we remove solvent completely, the simulations are pretty quick in comparison to atomistic simulations. So, there is a method called the Brownian dynamics method, which is going to be the high friction limit of the Langevin equation. So, at high friction, what we can do is we can eliminate the inertia term. The inertia term is going to be negligible, that is the p dot term, that is basically mass times acceleration, is going to be negligible in comparison to the friction term, and therefore, I can pretty much remove that, it becomes 0. Everything else is pretty much same as the Langevin equation, and what we then have is a simple first order differential equation in terms of the r dot, that is the velocity of the particle. So, acceleration is set to be equal to 0, and again using zeta equal to kBT by d, I can also write in this particular form. Again, the methods of numerical integration are very similar to Langevin equation, but Brownian dynamics is somewhat simpler because we are not dealing with the second order term, we are solving a first order differential equation, but it is only applicable when the friction offered by solvent is very large, where we can ignore the inertia term or neglect the inertia term in the equation of motion. One of the things that we have to keep in mind whenever we move from the atomistic simulations to Langevin dynamics or Brownian dynamics is the definition of time itself becomes somewhat arbitrary. So, in molecular dynamics with the solvent and everything, the time is well defined. As soon as we remove the solvent, of course, the motion is going to be faster because the solvent is not present, there is no collision with solvent. So, molecules can go very easily because there is nothing in between them, the solvent molecules are not there, and therefore, that may lead to somewhat speeding up of the motion of the molecules. Now, in some way the friction term is doing just that. So, it is basically slowing the molecules down so that the time scales remain comparable to what should be if the solvents were there, but then we have to really consider that also when we are looking at the time in comparison to the actual physical time, and we have to carefully define our time step in a manner that is consistent with the friction term that we have added and the diffusion coefficient and the system under consideration. So, it really becomes one of the problematic areas in Brownian dynamics simulations. So, one of the methods that is pretty much similar to Brownian dynamics, but it approaches the problem from a Monte Carlo perspective is kinetic Monte Carlo simulation method, where essentially what we do is pretty much what we do in a typical Monte Carlo simulation or an equilibrium Monte Carlo simulations. For example, we can perform a Monte Carlo with a fixed step size A, but then we associate certain time to every Monte Carlo step, and saying that let us say if I do this Monte Carlo step, I go in time with so much. Typically, when I say a Monte Carlo step in this case, it refers to the trial movement of all the particles in the system, and the delta t happens to be proportional to the A square by d, where A is my step size and d is my diffusion coefficient. Both in Brownian dynamics and in kinetic Monte Carlo scheme, the d is typically taken as constant, but in reality the diffusion coefficient may also change as the simulation progresses. For example, a system starts to aggregate. Now, the diffusion coefficient is not going to be the same as the diffusion coefficient in the solution. Secondly, the diffusion coefficient that we are typically using are the self diffusion coefficient. Once we have a binary system or a ternary system, there will be many mutual diffusion coefficient of species A going through species B and so on, that really makes the process quite complicated. So, the methods in principle are best suited for one component system, where the diffusion coefficient can be approximated to be the same as the self diffusion coefficient, and that is the quantity that is also given by the Einstein's relation. As soon as we have more than one component, that is typical of us as chemical engineers, we have to be careful what diffusion coefficient should go here, and in principle we need to have methods that should account for the mutual diffusivities between the species under consideration. So, until so far we have accounted for only two effects of solvent. One is the friction offered by the solvent, and other is the thermal motion of the solvent or the collisions of solvent with the solute. But in many cases, particularly in the non-equilibrium scenarios, the hydrodynamic interactions are also very important, and in that case we have to revise the Brownian dynamics scheme to also account for the hydrodynamic interactions. And even though that is of more purpose in cases when we are having some kind of a flow situation, that need not be the case. Even in thermodynamic equilibrium, these aerodynamic interactions can be important in certain cases. So, in these cases, one way to include that is to have a notion of a diffusion matrix that somehow accounts for the aerodynamics of the fluid, and we modify the equation of motion. Now, I am writing the numerical equation that we solve for instead of the actual equation of motion, where the position of a particle is updated according to this rule, where we have a diffusion matrix as opposed to the diffusion coefficient in the earlier equation. And since it is going to be a changing matrix, it will change with time and with variables in the system. We also have one more term that is corresponding to del dot D, that refers to the changes in the diffusion coefficient. So, in this case, this matrix takes care of the HI effects or aerodynamic interaction effects in this particular case. We can write the components of this matrix as something like Dij, which will refer to basically the particle I and particle j in the system. And now, since for both particle I and particle j, they have 3 coordinates in x, y and z direction, this matrix for every particle will have 3 times 3 components, 9 components. So, in total we will have n into n matrix of 3 into 3 matrices, or we can say we have 3n times 3n diffusion matrix. So, each component of the matrix typically is represented as Dij, that itself is a 3 times 3 matrix, and there is a random term that has a 0 mean, very similar to what we had earlier, and the correlation is given as 2d delta t, simply an extension of the idea when we had a constant diffusion coefficient. So, one of the choice of D is the Oseen tensor. This is not the only possible choice. The reason why we have multiple choices is because there are certain approximations involved in there, and there are certain limitations of this particular tensor we are using, and you can read more references to learn more about what is the problem with the Oseen tensor, but this is the one that is most commonly used. So, it contains basically 2 different expressions for the pair of the same particle and pair of 2 different particles. For pair of the same particle, the Dii is given by kBt by 6 pi eta a multiplied with the entity tensor, where I is defined as essentially a diagonal 1 and all other off diagonal terms are 0. Eta is the viscosity and a is the aerodynamic radius that can be found from experiments. Dij for I not equal to j is given by something with a similar prefactor, but there is an 8 here. Again we have an entity tensor in the beginning, and then we have the dyad comprised of the unit vector for the distance between I and j, or displacement vector between I and j. The unit vector is defined as the displacement vector divided by the magnitude of the displacement between I and j. The del dot D is 0 for the Oseen tensor. That is the reason why it is commonly used, because you may recall in the previous expression we had an extra term del dot D. So, for the Oseen tensor case it will not appear, and the modified equation therefore, if I drop that term, is going to be this, which is somewhat simpler because we have dropped a particular term from the expression. There is another method called the dissipative particle dynamics method that also accounts for hydrodynamic interactions. In this case, again the equation of motion is similar to Langevin dynamics, but instead of v and w dot here, we have functions of the position and momentum that I write as capital V and capital W. In the earlier case, it was simply the velocity of the particle and the Wiener process, but now both of these are a function of the position and momenta of the particles, and actually all the particles in the system. In this case, the particles represent really the regions in the fluid, they may not be the individual atoms or molecules. So, what I mean in here, let us say for example, I am considering a fluid, I am not really meaning that these particles are the ones which are being tracked, but these are referring to spatial regions in the fluid that are moving together, some kind of like collective motion of the entire region of fluid. So, it is happening really at a meso scale. So, there is not a very clear atomic scale analog whenever we are doing a dissipative particle dynamics simulations. And the reason why that happens is because the time scale for hydrodynamic interactions are quite different from the time scales where molecular scale processes take place. So, although in principle they account for some effects like thermal fluctuations and so on, and solute interactions and so on, but it does not really account for the detailed molecular resolution of these systems, and many of that is missed by assuming that the particles are not really the molecules, but regions of the fluid comprised of many molecules or atoms. The force between these particles that we defined are typically much softer. One of the most commonly used form is the following. So, the force pretty much goes like this with distance, it is a linear form, and that pretty much means that the particles can pretty much overlap, unlike for example, a Lennard-Jones interaction where you have substantial repulsion at a small r, actually a very large repulsion once they come very close. In this particular case, there is not really very large repulsion even when we go to r equal to 0, and therefore, what we can say is that the potential is very soft, and the consequence of that is we can take larger or longer time steps in our simulations. The reason why we could take only smaller time step is also because if I take a longer time step, we can violate many overlaps or we can violate many hard core of the molecules. But in this particular case, since we are working with softer potential, the overlaps are being allowed, so the particles can move with much longer time step than we can take in a say a molecular simulation. So, with this particular idea, I can define the force between the particles in one of these ways is this. So, we have a repulsion parameter A. We define a function of Rij by Rc, where Rij is again the distance between the particles, Rc is some cutoff distance at which the force goes to 0, and the function phi is defined as 1 minus x for x less than 1, that is pretty much the form of this is going like 1 minus x, and 0 after that. So, it goes to 0 beyond r equal to Rc. So, with this I want to conclude this lecture. In the next lecture, we will discuss some more methods of mesoscale simulations that also tries to capture the effect of hydrodynamics in somewhat different manner. Thank you.